the technique of partial fractions, which is good when we have this situation. We've got an integral of what we call rational functions. So some function of x on the top, some function of x on the bottom, and they're both polynomials. How do I approach it? Well, the first thing I do is, if that degree of the numerator is more than the degree of the divisor, or equal to, then I'll do a polynomial division first of all. Then the fraction that remains will have something where the degree of the top will be less than the degree of the bottom. So once we've got it in that situation, where the degree is less than, we go and factorise the denominator. We break it into its factors. Because what we're going to do is we're going to get this algebraic fraction, and we're basically deconstructing it into the individual fractions that it came from. So it's like our algebraic fractions questions in reverse. Normally we see two fractions and we add them together and get one. So we're deconstructing it back again. Now, to work out what those fractions are, for every linear factor, we must have come from a fraction. And the top of that fraction, the order will be less than the bottom. So it must be a constant number, because if the denominator is a linear factor, then the top must be a constant number. So we know, okay, we've got something on the top of x minus a. Now, if you have multiple linear factors, maybe you have x minus a squared, then you create a fraction for each of them. One for the x minus a, one for the x minus a squared. But you keep a constant number on the top of those. The only other possibility is it might be a quadratic that can't be factorised. And in that case, well, the order of the numerator has to be less than the denominator, so I put a linear on the top, so ax plus b. Impossible to be anything else, because all polynomials can be factorised down to be a combination of quadratics and linear factors. Start off with x squared on x plus 1. This is one where we just do a polynomial division, because we've got a quadratic on the top, a linear factor on the bottom. You might be able to just look at it and write it down, but if not, do yourself a polynomial division. So x and x squared goes x, then x into negative x is negative 1, leaves me with a remainder of 1. So this can be written as x minus 1 with a remainder of 1. So plus 1 on x plus 1. And everything there can be integrated. So the x goes to x squared on 2, the 1 goes to x, and the fraction is a log function. So we get the log of the absolute value. 3 on x squared minus x. I don't need to do a division, because the order of the top, well, it's a constant number. The bottom we have a quadratic. So we factorise the bottom. And so just a common factor of x. So I have x minus 1. So I want to know, what were the two fractions that we added together to get this? It must have done something like this. I have one fraction which is over x and one fraction which is over x minus 1. We added them together and we got the answer 3 on x minus 1. We just have to work out what a and b are. What are those two constant numbers? Let's multiply by the x minus 1, get rid of the denominators, and this is the equation we have to solve. But we can solve it by using clever substitution, because if I make x equal to 0, then the b goes away. And that gives me that negative a is 3, I now know a is negative 3. My next substitution, well, I'll make x equal 1, and that makes the a go away. And I'm left with b equals 3. I now know the two numbers. That means that our original fraction must have come from these two added together. And they both ended up being log functions. And here's the thing. It's always going to be a log function when you're talking about a linear denominator with this. Because remember, we're setting up a situation where we'll have a constant on a linear function. And that's always going to create a log. In this case, we have minus 3 log x plus 3 log x minus 1. Now, when the coefficients are the same number, don't worry about the plus or minus, but when they are the same, in this case it's 3, we'd usually, well, let's use our log laws and pull it together into one log. So the negative would go on the bottom because we divide, and the positive would go on top. So I have 3 log x minus 1 on x, and of course plus a constant. Quadratic denominator, linear function on top. So again, no need to do a polynomial division with this one. But can that bottom be factorised? And yes, it can. So this is another one that came from two fractions, both of which have a linear denominator. So let's see what we end up with. So in this case, a on x minus 5 plus b on x plus 2 will equal x plus 5 on x minus 5 x plus 2. Okay, well, again, clever use of substitution here. I'll make x equals negative 2, that'll make the a go away. B is negative 3/7. Now I'll make x equals 5, the b goes away. A is 10/7. Sub back in, and once again we'll end up with a log situation in both of these fractions. So I have 10/7 the log of x minus 5 minus 3/7 the log of x plus 2. I didn't bother using my log laws here because the coefficients were different. Now I could have, because remember you can always pull those constants into the logs. I could have made this 1/7 the log of x minus 5 to the power of 10 minus 1/7 the log of x plus 2 to the power of 3, then they both have a 7th out the front and pull it into 1. I just didn't see the point in doing that, so I just left it like this. Dx on x cubed plus x. Ooh, well x squared plus 1 won't factorise. So our fractions this time, we have a on x, so there's a linear denominator, but the next one's going to have a quadratic. That means on the top we get bx plus c. Let's work out what a, b and c are in this case. Well, the first one I'm going to do is I'm going to make x equals 0. Because if I make x equals 0, the bx plus c goes away. I can work out a. A is 1. How do I make the a go away? Well, I can't with real numbers, so let's use an imaginary one. If I make x equal to I, then the a goes away. I end up with minus b plus ci is 1. The real part must equal the real part, the imaginary part must equal the imaginary part. So b is -1, c is 0. Let's now go back to our fractions. Yes, the first one will be log because you've got 1 on x. The second one's going to be log as well. The derivative of x squared is 2x. So it's a log situation. We have the log of x minus the half of log of x squared plus 1. Again, you'll notice I didn't put the absolute value signs in on the second one because I know x squared plus 1 is always going to be positive. But it's not wrong to put the absolute value on there, I just didn't worry about it. Alright, here's one that's already factorised for me. But we notice we have the x plus 1 squared, so we have a repeated root on there. We have to create a fraction for both the x plus 1 and the x plus 1 squared as well. And we have a third fraction, x squared plus 1, which will have a linear function on the top, and all of that equals our x on x plus 1 squared, x squared plus 1. Whoa, alright. What will I substitute in here to make life easy for myself? First one I'm going to do is -1 because that'll make the a disappear. It'll also make the cx plus d disappear as well. So I'm left with b is -1/2. Well, now I'll do the I, because that'll also make the a disappear, but now the b will disappear. That ends up being -2c plus 2di is I. Real part must equal the real part, imaginary part must equal the imaginary part. So I get the c is 0, d is 1/2. I still haven't got b. I can't do something clever and make something disappear here. But at least I now know what b, c and d are. So I should be able to work out what a is. Make life easy for yourself. What's the easiest number to substitute in that I haven't already substituted in? Well, it's got to be 0. Sub 0 in, I get 2a plus b plus d is 0, but I know what b and d are, so now I can work out a. A, all that work for nothing, you could say. A is 0. Substitute in. There are our two fractions that this came from. Okay, now we can integrate these. I've got -1/2 x plus 1 squared. Well, that's just an add 1 to the power over the power. The second one is going to be an inverse tan situation. So I have 1/2, 1 on x plus 1, plus the inverse tan of x. Now, I'm going to show you another way of finding these constants, commonly known as the cover-up method. So when you've got all these linear denominators equals some overall functions, there's a very quick way of doing it. To work out a, what you do is substitute a into this function, but you cover up the factor that would become 0, which in this case would be x minus a, because that's what I'm trying to work out, is the a. And then that will give me the answer. To work out b, I cover up the x minus b and substitute in. To work out the c, cover up the x minus c, substitute in, and so on for all of your linear ones. So let's go back to the ones we just saw and see how much quicker this could be. So alright, I want to work out a. So I cover up the x and substitute in what would make it equal to 0, which is 0. Now I put the working out down, but you may well just go straight to the answer with something like this. So it would be 3 on 0 minus 1, which is negative 3. To work out the b, I would cover up the x minus 1, substitute in what would make it equal to 0, and I get 3 over 1, which is 3. And there's the two numbers. Then the second one we looked at, so again the same idea. To work out the a, I'm going to cover up the x minus 5, substitute in what would make it 0, which is 5. We get 10 on 7. To work out the b, cover up the x plus 2, substitute in what would make it equal to 0, or negative 2 would, and we get minus 3/7. There's the number. Now, most people, when they show you this, say, oh, this is only for linear denominators. And that's not true. You can do it for quadratic ones as well. You can do it for all sorts of things by making the use of complex numbers. So we looked at this one. Well, the first one's fine, because I can do it the same way. Cover up the x, substitute in what makes it equal to 0, which would be 0, and I get the a is equal to 1. Applying the same idea, all I do is cover up the x squared plus 1, substitute in what would make it equal to 0. Well, I would make that equal to 0. So I get bi plus c is 1 on I. The reciprocal of I is negative I. I've got b is negative 1, c is 0. Now, it might mean more work doing it this way. But that's right. You could also use a combination of ideas as well. Maybe I'll just use the cover-up method to get those linear ones out. Maybe I'll do clever substitution to do the other one. I mean, the choice is yours. How about this one? Okay, well, to work out the a, I can cover up the x minus 1, substitute in what makes it equal to 0, which would be 1. So a is 1. Ooh, now for that second fraction. Now this is where maybe this is not the best way of doing it, but you could do it this way. Cover up the 4x squared plus 1. What would make that equal to 0? Well, I on 2 would make that equal to 0. Okay, so I'll substitute in I on 2. Ooh, bit of work to do on the right hand side now. Eventually, after a lot of manipulation, we get there. It is 1 minus 3 on 2i, therefore b is negative 3, c is 1. I'm not saying that's the best way to go for this one, but I am showing you that, hey, the technique still works. The idea is still good, but maybe there's a better way for this one. Maybe the clever substitution was a better way of approaching that one. Well, what about the multiple factors? And as I've said here, yeah, it can be done with multiple factors as well. It just requires a little bit more work. So we had this one where there was an x minus 1 and the x minus 1 squared. Cover up the x plus 2 and I can get the a. That's negative 2. Oh, but hang on, I've got x minus 1 and x minus 1 squared. Which one do I cover up? Well, I cover up the one that's on the right hand side. I'm covering up the x minus 1 squared. But which answer will it give me? It will give me c, because it's the one that has x minus 1 squared. So c will be, substitute in what makes it equal to 0, 1. I now know c is 3. I can't use it to find b. I can only use this method to find the higher power. The fraction involves the higher power. But that's okay, because I've got a, I've got c. Now I'll go back to the idea of, oh well, let's just do a clever substitution. Let's substitute in a number I haven't used. Well, 0 I haven't used. It's always easy to substitute in. And then I can work out, there we are, b ends up equaling 2. I can get the other one that way. Oh, okay, let's look at this one that we did. So we have x plus 1 squared, and x squared plus 1. Wow. Okay, let's work out b, it's the higher power. Cover up the x plus 1 squared, substitute in the negative 1, I get negative 1/2. There's b. Let's do the x squared plus 1. Cover up the x squared plus 1. What makes that equal to 0? Well, I does. Substitute in I, we get c is 0, d is 1/2. Now I just do a clever substitution. Just use a number I haven't used. I'm always going to go for 0 if it works. The only time 0 is not going to work, of course, is if you end up with 0 on the bottom of the fraction. So x equals 0, a plus b plus d is 0, a is 0. We've got our constants. So that's making use of both ideas there. What about if you end up with a quadratic denominator that can't be factorised? I guess my answer is, well, gosh, don't use this method. But it does work. Here we go. X squared plus 4x plus 5. Well, let's do the easy one first. X plus 1 I can do. The method will work for that. Cover it up, I get a as 1. So the question is, if I was to cover up the x squared plus 4x plus 5, what would make that equal to 0? I could complete the square and solve this. It turns out that, well, there it is. Minus 2 plus I. That's what I'll substitute in. Alright, substitute in minus 2 plus I, and well, eventually we get there. B is -1, C ends up being -3. A lot of work for that one. Maybe clever substitution is a better way to go. I guess it all depends on the numbers that it turns out to be. I mean, I suppose finding that minus 2 plus I wasn't too bad, but you could imagine some of those answers might have, you know, a half plus root 3 on 2I or something like that. It's, too much work, thanks very much. Alright. So we're going to look at the idea of partial fractions, so deconstructing our fraction down to the parts that it came from.